The science behind a PET scan. Hi, and welcome back. This video series will help you understand step by step how a PET scan works. Make sure to watch the videos in the correct order, as the information in each video builds upon the previous ones. Here you can see the journey we are on to understand the science behind a PET scan. In the previous video, we talked about synthesizing the radioactive tracer. In this final video, we'll look at the creation and analysis of the images. The other videos are linked in the description box down below, so if you've skipped a video, make sure to check out the others. Today, we'll talk about receiving the images and how to interpret them. Again, we'll start off with a repetition. Next, we'll look at what happens when the radio tracer is injected. Then, we'll talk about the special detectors that pick up the gamma rays. We'll see how the images are reconstructed, followed by the interpretation of them. In the end, we'll summarize the most important concepts of this video, and then round it off with a summary of everything you have learned during the entire series. A radio tracer is made up of a radioactive isotope and a molecule. A cyclotron accelerates charged particles to high speeds and shoots them at a stable isotope, creating a radioactive isotope. The most common tracer is FDG, where deoxyglucose is labeled with F18. A short half-life comes with pros and cons. For instance, minimizing the health risks, but also requiring on-site production. The patient is asked to remove all jewelry and wear a hospital gown. Then, the tracer is injected intravenously. The patient has to wait around 30 to 90 minutes for the cells in the body to absorb the tracer. When the tracer has been absorbed, the patient lies down on the bed that slides into the machine. The scan itself takes around 30 minutes, and the patient is advised not to move during that time. Let's find out what happens when the tracer gets injected into our bloodstream and the radioisotopes start decaying. I hope you can all recall what a beta plus decay is. Those who explained it to themselves whilst making their bed, as I instructed in video 2, will know. If not, I'll remind you. It's a specific type of decay where an unstable nucleus emits a positron and a neutrino as a result of decaying. The positron is our main player here. So imagine the radioisotopes in the tracer are decaying and they are all emitting positrons. This is the key part to understanding how a PET scan works. Remember from the second video that everything is made up of atoms? Our bodies are made up of many atoms, and because atoms contain one or more electrons, there are many more electrons than atoms in our body, as shown on the screen. When the positron has been emitted and has traveled its short path through our body, which is about 0.5 millimeters for F18, it collides with one of the many electrons that are found in our body, as we talked about before. The collision of the positron with the electron leads to them annihilating each other. This is the positron traveling its short path through the body, and it will collide with the electron in just a moment. Imagine the annihilation as two particles coming together to form something new. This annihilation happens because the positron and the electron are essentially the same particle, just oppositely charged. One often uses the term antimatter or antiparticle, meaning that the positron is the antimatter counterpart of the electron. Let's see what the annihilation looks like. As soon as these particles collide, their rest mass is converted into energy. As a result of this, two gamma rays with an energy of 511 kilo-electron-volt each are emitted in opposite directions. The photons are what the detectors pick up in order for the images to be obtained. In reality, not all the photons reach the detectors, leading to a reduction in the signal intensity. The reduction of signal intensity is called attenuation and depends on the tissue thickness between annihilation site and detector. An individual or single unit scintillation detector consists of three parts, namely a scintillator, a photocathode, and a photomultiplier tube. The scintillator is a crystal that faces the patient. Attached to the end of the scintillator are one or multiple photomultiplier tubes. The photocathode lies between the scintillator and the tubes and is depicted by the blue surface in the image. The red line is where the photocathode lies, just to clarify. The gamma rays generated by the annihilation events are absorbed and then get converted into electric pulses in order to obtain the images. Let's look at this step by step. First, the scintillator absorbs the incoming gamma ray. The high energy gamma ray then gets converted into low energy photons. These low energy photons can either be visible or near ultraviolet light. Then, in the photocathode, the low energy photons are absorbed and electrons are emitted. So, simplified, a photocathode converts visible light into electrons. These electrons then enter the photomultiplier tube. As its name suggests, in the photomultiplier tube, the electrons are multiplied exponentially. This results in a strong current pulse at the end of the tube. These current pulses are sensed by electronics connected to the end of the tube and allow the computers to reconstruct the images. The detector we looked at before is a single unit detector, and 8 of these detectors are combined to form a module. Modules are arranged in a ring, known as the detector ring, that absorbs the gamma rays and allows for the creation of 3D images. However, the detector ring doesn't consist of only one ring, but of many rings placed next to each other to form one thick ring, similar to a donut. The next step is acquiring the data before the computers can reconstruct the images. The point of annihilation is measured as follows. Remember our 2 gamma rays from before? When those oppositely incoming gamma rays are absorbed by 2 scintillators at the same time, the computer will connect those points by drawing a line of response. Where the majority of these lines, stemming from many different annihilation events, intersect, is where the highest activity of the radioactive tracer is found. A good example for this would be a tumor. Due to a tumor's high metabolic rate, the lines would intersect where the tumor lies. Sometimes false lines of response can be detected. These are called background events and are distinguished as either random or scattered coincidences. We'll only be looking at the scattered coincidence. This happens when, for instance, 2 photons are detected, but the location of the annihilation event is incorrectly identified. You can see how this happens on the screen, where the true annihilation event is the dark gray circle, and the gray arrows are the photons. The lower photon did not continue in a straight direction, but probably interacted with tissue in such a way that it got diverted from its original path. The red dotted line is where the computer then draws the false line of response, which results in an incorrect determination of the location of the annihilation event. These false lines show up on the images as noise in the background. That is why corrections almost always need to be undertaken to obtain the final images. The next step after acquiring the data is to reconstruct the images to see what's going on in the body. The data we acquired before is fed into computers that then reconstruct the images with the help of complex algorithms. We won't go into the details as they are beyond the scope of this video. We will keep it simple and look at a few basic steps in order to understand the principle. The first thing is smoothing out the image in order to reduce noise. This image on the screen is actually from a CT scan, as I couldn't find a decent picture from a PET scan. Just imagine this were from a PET scan, as the principle of smoothing out the image is the same. The images above are before smoothing out, and the images below are after. Secondly, an artificial color scale is often added. This helps enhance the visibility of the affected areas by increasing the contrast. However, this step is not always done. A third possibility is to combine the image of a PET scan with a scan from another imaging technique, for instance, from a CT scan. This allows the doctors to analyze the body from a metabolic and an anatomical point of view. As we learned in the introduction video, this is now almost always done by a PET CT scanner, which creates a combined image. It's not commonly done with separate scans anymore. Here you can see an animation of the reconstruction of a PET scan. This animation is from humanhealth.org. And it looks fascinating, right? After the images have been reconstructed, they need to be interpreted correctly by a specialist. The images give the specialist an overview of the patient's health and allows for starting or continuing a treatment. We'll look at 2 reconstructed scans together. Of course, I am by no means a doctor and do not have the qualifications to make medical judgments based on a scan. We will be using what we have learned in these videos and applying it to scans where the findings are already known. This is a full-body PET scan of a woman where the tracer FDG was used. According to Wikipedia, this scan shows a large metastatic tumor mass in the liver from colon cancer. This can be seen by the red spots within the abdominal region of the scan. The radioactive urine in the bladder means that the body has already started to break down the tracer. That is why the bladder appears red on the scan. The bladder, kidneys, and brain are accumulating the tracer normally. Let's look at the next image. I find these scans fascinating. On the left, we can see a brain with healthy metabolic activity. The brain in the middle is already slightly impaired in comparison to the first brain, and the brain on the right is affected by Alzheimer's disease. Alzheimer's causes the hippocampus, the part of the brain responsible for memory, to shrink, leading to difficulties remembering things. The PET scan was done to find out if there were any amyloid beta plaques, a typical feature of Alzheimer's disease, in the brain. The darker regions of these brain scans are where there is plaque, and therefore no metabolism of the brain cells in those areas. Let's sum up what we learned today. The result of a positron and an electron annihilating each other is 2 gamma rays. The gamma rays are absorbed by scintillators and are converted to strong current pulses. A detector ring consists of multiple rings that are made up of modules. The images almost always need to be corrected in order to receive accurate quantitative information. In my opinion, these are the 4 most important facts about PET scans that I want you to remember. A PET scanner uses small doses of radioactivity to detect diseases. A unique feature of PET is measuring the metabolism of cells in the body. The radioactive tracer is tailored depending on what the doctors are scanning for. The procedure is pain-free and non-lasting, so after the scan, you are good to go. Wow, we are already at the end of the journey. I hope you guys enjoyed it and that you now know how a PET scan works. Let me know in the comments what your favorite part of the series was. And remember to repeat things a few times here and there to make sure you remember what you have learned. Thank you so much for listening.